Hello students. So in disconnection approach series, today I will discuss regioselectivity in disconnection approach. In previous lecture, I told you about the chemoselectivity in disconnection approach. So one of the example that I took, that is the preparation of paracetamol as a target molecule. So this paracetamol, it can be prepared in lab by the acetylation of para-aminophenol. So if we have para-aminophenol, then this para-aminophenol molecule has two functional group. So out of this two functional group, only this more reactive NH2 functional group will undergo acetylation, whereas OH will not undergo acetylation. So this is the acetylation of this para-aminophenol is the example of the chemoselectivity. Now today you will see the regioselectivity. So how can we define this regioselectivity? As when one side of functional group react in preference to the other side. Okay, so when one side of functional group reacts in preference to other side to give major and minor product. Product is called as regioselectivity. Okay, so two products will be formed. One would be major and another would be minor. Suppose if only one product is formed and that is 100% product is formed, then that is called as the regiospecificity. Okay, now so let's take the example of regioselectivity. Now suppose if you have this phenol, then this phenol in presence of base, suppose I take sodium hydride, then it will give you phenoxide ion. This acidic hydrogen that will be taken out and you will get the phenoxide ion. Now this phenoxide ion has a resonance stabilized structure and we can write it as minus charge over here. Now if we do the methylation of this, in presence of methyl iodide, so this has minus charge, this has plus charge. So this methyl will react at the oxygen center, not this carbon center. So the product that would be formed is this. So all we can say that here O alkylation has taken place, not the C alkylation. So this is O alkylation of phenol. O alkylation of phenol has taken place, not the C alkylation. Now suppose if we have ketoester, now this in presence of base, suppose if we have sodium ethoxide, then it will grab this acidic hydrogen from here and it will give you minus charge over here. Now this can be converted into enolate ion Now if we do the methylation, then in this case the methylation will occur at the C center. So here also we have two center, that is this O center or this is C center. So here the methylation will occur at the C center, not the O center. So this is an example of regioselectivity. So here we can write C alkylation has taken place. Now let us disconnect one of the target molecule. So if we take, I am writing the retrosynthetic analysis of one of the target molecule. So let's take the target molecule as okay, this is one of the unsymmetrical ketone. Suppose if we want to synthesize this, or this is our target molecule, and if we do the disconnection. So disconnection can be done either from here, or disconnection can be done from here. Suppose this is side A, this is path B, and this is path A. Now which path will be taken first, either A or B? So we should take path A first, means this CC bond that should be disconnected. So reason for this is when we disconnect this via this path, then we will get okay. So this disconnection occur via path A. Why? Because first of all you will get the benzyl cation being the more stable. In this case, if you do the path B disconnection first, in that case you will get the propyl cation. Okay, so benzyl cation being the more stable, it will disconnect first. So now the disconnection, you will write the disconnection via path B. So this disconnection will occur, and you can write the two synthones that will form. It means this will have the positive charge, this is negative charge. So this negative species synthone is formed, and you will write the, for particular this, the synthetic equivalent, that is this ester group you can add here for the synthetic equivalent, and another synthetic equivalent, that is propyl chloride, you can write. Now, so this is the retrosynthetic analysis of this unsymmetrical ketone. Now if you want to write the synthesis, then you will go in a reverse direction. So first of all, take these two synthetic equivalent, you will get this, then react it with this synthetic equivalent, finally you will get this unsymmetrical ketone. So let's write the reverse reaction. So first of all, this is the active methylene compound, this in presence of sodium ethoxide. So this will grab this acidic hydrogen from here, and you will get minus charge over here. Now you have this propyl chloride. Now the SN2 reaction will occur. You will get so this part will here add over here. Now again this molecule has one of the acidic hydrogen. So this in presence of sodium ethoxide, base will extract out this acidic hydrogen, and you will get the negative charge So now this nucleophile, this will attack over the your benzyl chloride. So you are getting this target molecule. Okay, so here this regioselectivity, you can see the regioselectivity, all this reaction is taking place at one side of functional group. So this side is remain unreacted. So this is one of the example of regioselectivity. Now let's see the regioselectivity in alpha beta unsaturated ketone. So let's take another example. Regioselectivity in alpha beta unsaturated ketone. Okay, so if I take one of the examples, so in this case the nucleophile on this alpha beta unsaturated ketone can add in two ways. One is the direct addition. One is the direct addition, or it is also called as the 1,2 addition. So let's take one of the example. If you have this alpha beta unsaturated ketone, so you have this alpha beta unsaturated ketone, this is alpha, this is beta. Now, so this alpha beta unsaturated, we can number it as 1, 2, 3, 4. This is suppose first position, second, third and fourth. So the nucleophile can add, or the reagent can add over 1, 2 position. Then it is called as a direct addition. Or the reagent can add over 1 and 4th position. And that is called as the 1,4 addition or conjugate addition, or it is also called as the Michael addition. So suppose if we have the nucleophile, then nucleophile, if it's add over this one at this electrophilic center, then you will have okay, and now this in presence of this, suppose after this workup you will get this product. So this is 1,2 addition product. This is 1,2 addition product. And this product is kinetically favored. This product is kinetically favored. Okay, now second type of addition, it may be indirect addition. Indirect addition. Or it is 1,4 addition, or we say Michael addition. It is also called as the Michael addition. Now, suppose this was R1, this was R2. Now, so the nucleophile can also add at 1 and 4 position. Okay, so we can write this as So positive center will develop over here and nucleophile can add over here also. So this nucleophile can add over here also. Okay, and double bond. So we can write it. So this is enol form, and we can write it in a keto form also. So as you can see, so after this workup, okay, followed by workup, you will get this product. So this is 1,4 addition product. And this is thermodynamically stable. Stable product. Now, what is the reason that here this direct addition is taking place, here this indirect addition or 1,4 addition or Michael addition, or we also say it a conjugate addition. It is also called as a conjugate addition because the reagent has attached at 1 and 4 position. Okay, so OH and nucleophile, this OH and nucleophile 1, 2, 3, 4th position. Okay, so that's why it is also called as the conjugate addition. Okay, so what is the reason here? Actually, here if you will see, then in this alpha beta unsaturated ketone, this part is, and we have 2 reactive centers. So carbon carbon double bond. So this is your strong bond. This is strong bond, and this bond is the weaker bond. This bond is weaker bond. So in this case, the strong, if nucleophile is the strong one, and if nucleophile is the strong nucleophile, or we can say hard nucleophile, this nucleophile being the hard, it will attack at this strong center. So this is hard. So hard nucleophile will add over the more more reactive. This hard nucleophile being more reactive, it will attack over the strong center. Okay, so in this case, this nucleophile should be soft nucleophile, and it should attack the less reactive center. And you know, this less reactive center, this carbon-carbon double bond is the less reactive center here. So it will attack over here to give the 1,4 addition product. Okay, so we should know about this hard nucleophile and the soft nucleophile, which is the hard nucleophile and which is your soft nucleophile. So let's differentiate the hard and soft nucleophile. So as you can see, this hard nucleophile, it attacks at the strong center. A soft nucleophile, it attacks as a weak center. So hard nucleophile being more reactive, and it is having the higher energy, so it will give you the kinetically favored product. Soft nucleophile, it is attacking over the soft center, okay, weak center, so it being the less reactive, it will give you the thermodynamically stable product. So so this is the Michael product. This is the Michael product, 1,4 addition product. So let's differentiate between this hard and soft nucleophile, and then we will take a few examples. So let's see the difference between the hard and soft nucleophile. Hard nucleophile and soft nucleophile. Hard nucleophile and soft nucleophile. So what I told you, this hard nucleophile hard nucleophile is more reactive. This is more reactive. This is less reactive. And this is small in size. Small in size. This is large in size. So as this is larger in size, so that's why it would be, no doubt it will be more polarizable, and this is less polarizable. Okay. Now, so as this is more reactive means that would be less stable, and this will be more stable, you can say. Okay. So it will attack at the strong center. It attacks at strong center. For example, you see for example the C double bond O center. So it attacks at weaker center. It attacks at weak center. For example, as you saw, C double bond C. Okay. Another example. So here the negative charge, in this case for this hard nucleophile, the negative charge is localized in the nucleophile. So negative charge is localized on nucleophile. Negative charge is localized on nucleophile, whereas here negative charge is delocalized on nucleophile. Okay, so as it is less stable one, so that's why it is okay. So it will give you the kinetically favored product is obtained here. Here you will get the thermodynamically favored product. Thermodynamically favored product. Okay. So these are the very important points. So hard nucleophile is more reactive and it will attack at the strong center. Okay. And soft nucleophile, being less reactive, will attack at the weak center to give you the thermodynamically favored product. Now let's see some example. For example, if you see, for example, this lithium aluminum hydride, sodium borohydride, okay, or this OH minus. These in here, the negative charge is localized over the nucleophile. Here the H minus being the nucleophile, negative charge is localized. Here H minus being the nucleophile, negative charge is localized. This ethoxide ion charge is being localized, so that's why this is a hard nucleophile. Similarly, in this case, or some smaller size nucleophile, like if you have a fluoride ion or chloride ion, this also act as a hard nucleophile. Whereas here, for example, we have the organo copper compound, that is Grillman's reagent. Okay, organocuprate. This organocuprate, this acts as a soft nucleophile. Okay, organocuprate, or this is the Grillman's reagent. Similarly, some other example, for example, if you have a large size atom that act as a soft nucleophile. So for example, this bromide, iodide. Okay, or sometimes this in this cyanide ion, where as you can see on large nucleophile, and this large nucleophile the negative charge is delocalized, so that's why this act as a soft nucleophile. Large atom, more is the size, then negative charge is delocalized more, so this will act as a, here also in cyanide the negative charge is delocalized over carbon and nitrogen center, and in the same way this enolate ion also act as a soft nucleophile, because the negative charge is dispersed or delocalized over here this oxygen or this carbon atom. Other examples, like here you can write Grignard reagent, so these are some of the examples of hard and soft nucleophile. Okay, so what I told you, hard nucleophile being more reactive, it will attack at a hard center where the carbon oxygen, which is the strong bond, whereas soft nucleophile it will attack as a soft center like weaker bond, carbon carbon double bond. Now let's take one of the example. So this is alpha beta unsaturated ketone, and this in presence of, suppose if we write this RMGX here, or if it is reacted in presence of this Gilman's reagent, then what should be the product here? In presence of, if you have alpha beta unsaturated ketone, in presence of this and this, what should be the product? So as you know, this RMGX is a hard nucleophile. So hard nucleophile, it will attack at a hard center, that is carbon oxygen double bond. So here the product would be, so this double bond, this carbon carbon double bond will remain intact, whereas the attack will take place at carbon oxygen double bond, and you will get the product, final product. This is your final product. Okay. Now this in presence of this Gilman's reagent. Now this Gilman reagent, as I told, this is a soft nucleophile. So soft nucleophile attacks at a weaker center, that is carbon carbon double bond. So the product would be, here you will get this product. Okay. Now let's take one of the example of this retrosynthetic analysis. I will take this retrosynthetic analysis of one of the alpha beta unsaturated ketone. Suppose I have this. So I am taking the gamma delta unsaturated ketone. I am taking the example of gamma delta unsaturated ketone. Let's see the disconnection of this. So this is position 1, 2, this is 3, 4, 5, 6, like this, or otherwise this is alpha position, this is beta position, gamma position, this will be the delta position. Okay, so let's take the disconnection. So from where this molecule can be disconnected? No doubt we will not disturb this 6-membered ring, we will not disturb this carbon oxygen double bond. It can be disconnected from here. Okay, it can be disconnected from here. And what should be the synthon? The synthon formed would be here. This will have the negative charge and this will have the positive charge. Okay, because this is negative, positive, negative, positive, like this. So what you can write? So the negative charge here you can write the RMGX, or we should write here the organocuprate. So that can be converted into organocuprate. So we will write organocuprate plus. So this synthon here, positive charge is present over here. So positive charge is present at the third carbon from this carbonyl carbon 1, 2, 3. So if positive charge is present over here, then the synthetic equivalent that we will write, the synthetic equivalent will be, this should be the synthetic equivalent, and you are getting alpha beta unsaturated ketone. Okay, and here we are writing the organocuprate. So this is converted into this allyl anion. This allyl anion is converted into organocuprate, not this RMGX. Okay, so why? What is the reason? That this allyl anion in size, it is a big size. So big size. So if it is a big size, then as all of you know, this is a soft Werner's center. So soft interaction. This is the allyl anion that will interact with this copper. So both the soft interaction by HSAB principle. So that's why we should write here the organocuprate, not this RMGX type of reagent. So we should write here this. Now from here we can write the synthesis. So if we write the synthesis in a reverse direction, if you write the synthesis in reverse direction, then okay. So this being the positive, this being the negative. Okay. So this will attack over his center. So no doubt, if a nucleophile is soft one, if nucleophile is softer, then it attacks at the carbon-carbon double bond. So that's why it will attack at this carbon-carbon double, that is weaker center, not the strong center. So now in this case, the target molecule, you will get the same target molecule. So you are getting this target molecule. Okay, so this is about the regioselectivity in disconnection approach.